I am Pascal, ETP4HPC's communication manager. I usually say that my colleague Gabriela is here to help me, but she's not. She was not available today manage on my own. So for those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation, JU. So today we are going to talk about quantum machine learning in HPC. And I see that it's a very interesting topic to everyone because we have a lot of people registered today. So before we delve into today's topics and before we introduce the speakers, I would like to share a couple of practical. The webinar is in listen only in our control panel that's illustrated here to ask questions. You can also download the handouts. The slides are already in the handouts section, so you can download them. And you can submit questions at any time during the presentation, but we'll handle them at the end of the session. So, today we are welcoming Max Kiefer Emanuelidis, but Valeria Bach is here to introduce him. Valeria is the one who really helped. So can you explain a little bit about today's topic and maybe introduce Max?
Yes, sure. So Max is a colleague of mine, and we have been working together for years now. He is amazing because he revolutionized almost the field. He has been working during his PhD on many body theory. That both at the University of Kaiserslautern, called RPTU in Germany, and at the University of Manitoba in Winnipeg, Canada. Now he is working on quantum computing mainly, and here with his speciality on quantum machine learning. So he's partly employed by DFKI, which is the Artificial Intelligence Research Institute in Germany, and partly by RPTU in Kaiserslautern. His research focuses on quantum machine learning, and he's developing a lot of algorithms to understand the limitations of current architectures. But in addition, and that's where I know him best of, he's also engaged in quantum education research, where we have been together organizing several summer and winter schools on quantum machine learning. He leads a research group of approximately 15 members and closely collaborates with Fraunhofer in Kaiserslautern, but also in Hamburg. And it's a pleasure to listen to him and his insights into quantum machine learning. He knows that everybody's also very interested in HPC and will try to also consider that in his presentation. So I hand over the floor to you, Max.
Thank you. Sorry.
Thank you very much, Valeria. And now
So the floor is yours, Max. You should be able to share your slides now.
So now let me. So can everyone see my screen? I think so.
Yes, and it's in slideshow mode. Perfect.
Yes. And you see my laser pointer, right?
Yes, we do.
Perfect. So thank you again, Valeria, for this very kind introduction. And as Valeria told you, I will be talking about quantum machine learning in HPC. And I will give you an overview and my perspectives on how the topic may develop, especially from a slight perspective of a physicist. And what I can tell you directly from the beginning, quantum and quantum AI and quantum machine learning is currently only possible to a certain degree with the help of HPC. Without high performance computing doing the scheduling between the quantum world and the classical world, there would be nothing possible. So Valeria already told you, I'm from the German Research Center for Artificial Intelligence. This is our beautiful building in Kaiserslautern. And same in the same city, we have the university, the so-called RPTU Kaiserslautern-Landau. And of course, here the sky is blue today also here. So I'm very happy that you joined in and listened to this talk. My current group is here on this picture, and we have focused on quantum machine learning, quantum education research in strong collaboration with the LMU in Munich, and quantum inspired models and optimization with the Fraunhofer ITWM. And the group is only partially here. As Valeria said, we are roughly 15 to 18 people currently. Furthermore, the school that Valeria mentioned, we have another iteration on a summer school for quantum machine learning. This will be in Bad Honnef this year in August. And it is in the physics center, and we have quite a lot of interesting speakers from the interface between computer science and physics. So quantum machine learning exactly, with support from IQM. And technically, it's your last chance to register for the school until the end of next week. So if you're interested and want to join, what I can tell you, we had a lot of fun in 2024, the so-called Quick Start 2024 in Kaiserslautern, then in 2025. And one would argue that we will do as many schools as we have people currently, and everyone will like sit down at the end at some point of time. Today, what I would like to talk is first the motivation of why we want to include quantum computing in HPC, or otherwise why we need HPC to do quantum computing. Then I want to show you a little short history on quantum machine learning and how the topic developed. Furthermore, I want to tell you current active developments, how to make the HPC and quantum computing processes very tight coupled, that we can actually do work with it. I will tell you a little bit about quantum error correction and why it is necessary for quantum advantage. And then I'll tell you a little bit about my physics perspectives. Starting with our motivation for quantum computing, probably because you also are here and want to listen, is if we have some problem, for example, solving a cryptographic key, here the RSA, quantum allows us to have an exponentially fast deciphering of this key in comparison to the high performance computer. So we can find a setup such that we need 10 to the power of 15 years on our current best exascale machine, but our quantum processing unit would only need 3 days to do the solution. This is one algorithm that has become the main driver for quantum computing. But on the other hand, we have to think also about new ways to do computing, because we get to the end of Moore's law scaling, and also to Amdahl's law, which means that doing parallel processes, how we do them classically, will yield not a linear improvement, but will actually saturate at some number of processes. Changing our computational model from classical computing to quantum, which just does a few things slightly different, may also allow us to do parallel computing completely different with the number of qubits than we do with the number of processes. And all of this, of course, is then thought about on AI topics, how we can then improve AI topics and machine learning. And therefore, the transition point is quantum machine learning. So where did quantum machine learning actually started? And this is quite old, if you think about it. It's from 1997. So in 1997, it was formulated the first ideas how we could write a quantum perceptron. but it has no connection to what we think of current quantum neural networks. But still, the first ideas were given. 2008 and 2009, we had the known HHL algorithm, which is currently the driving force for quantum machine learning. Similar to Shor's algorithm in quantum machine learning, HHL is important, and I give a next slide on that. And this yields to significant changes of using classical machine learning models on quantum hardware and getting a speed up. So we can argue that the current quantum machine learning topic started around 2014. And now we talk about variational quantum neural networks, quantum kernels, quantum generative models. All of that is here already in 2018 and 2019. And especially what I want to mention is around 2019, because here we had the first actual quantum computers that left the experimental labs and were, for example, deployed by Google, and also accessible to parts of these quantum computers, for example, from IBM, were also accessible to the public. So now you have these still to a certain degree experimental platforms, and you want to connect them to real problems. So the idea started of quantum computing integration into HPC. This was then in 2018, 19, and 20, where we just used the quantum processor as an acceleration unit. And we prepare everything on our HPC and then send it to it. Now in 2020, what we figured out is that the current, let's say, experimental hardware that is existing is, though interesting, but far away from any advantage because of being so noisy. And furthermore, the ideas on how to benchmark these problems was risen in 2021, 2022, and 2023, because in classical HPC, you know, for example, LINPACK, there is no quantum equivalent to have any form of true benchmark that can handle a true outstanding non-trivial problem. And what we currently have is also a lot of skepticism about the topic of quantum machine learning, because there are a lot of restrictions and very specific cases where quantum machine learning can be optimally applied. But let us think of these problems that we could actually speed up. And here the HHL algorithm, the driving horse for quantum machine learning, is a solution or gives us a solution for a sparse linear system. And it can do this and solve this problem exponentially faster than a classical model, considering it is also exponentially sparse. Again, we would need a classical HPC, 10 to the 15 years, and our QPU only 3 days to solve this issue. But this theoretical algorithm then leads us to a lot of exponential speed ups in linear algebra for machine learning clustering, kernel methods. For deep learning, as one would say, deep learning is mostly a black box. It's very difficult to say anything, especially if it's quantum in between. But one thing that we can show very nicely in most cases, and things that we can already get in many cases, is a polynomial speed up. Here I want to mention that only given a certain amount of assumptions, for example, that we have access to a quantum RAM, which doesn't exist yet, and we have exponential sparse problems, then we get this exponential speed up. But otherwise, we should rather think of a polynomial increase. How is current setups or workflows for HPC? And I call this a linear workflow. And here we have the quantum processor as just an accelerator. our HPC system is nothing else like needs to do a pre-processing. This can mean that we have an optimization problem that we need to bring, for example, in a quadratic form. This is so-called Kubo, quadratic quadratic unconstrained binary optimization. And then what we hoped for is that we just send it to the QPU, it gets the quantum speed up and returns us the results. Yeah. What I want to mention is that a quantum model or a quantum computer is stochastic, meaning it can evaluate a lot of paths in parallel, but the end solution of our system is just a bit string. We just return a bit string. So if we search for especially one bit string in a huge list, then we have to measure multiple times, thousands, 10,000s of times to get our solution. Now the problem arises that one may get an enormous overhead, as one would need to run multiple times. This is what we see in this workflow as well. We have a huge latency because not many quantum computers are available. Data has to be sent to the quantum computer, has to be transpiled, and for the whole workflow, I don't get any benefit. As long it was thought, and this was the opinion at the time, around 2020, 2021, that if we just have enough qubits, it doesn't matter even if they are noisy, we can get some speed up. So this is the so-called noisy and intermediate scale quantum error. Today, we know the more qubits we add, the problem just becomes too noisy. We don't see any benefit, especially if we have these huge latencies. One solution is quantum error correction. And here what you can think of quantum error correction is just name dropping here color codes and surface codes, which lead to some form of embedding such that these qubits here on the surface or around the other ones correcting this the qubits in the middle. With this idea, we get a new overhead of quantum error correction, but we get the benefit that our solution is not completely random. So this linear model is therefore still somehow possible when quantum error correction does not give us a too strong overhead. In the recent past, what has been done is, of course, to use more HPC power and classical AI to do this error correction in the form of error mitigation, learning error patterns the quantum computer can have given noisy qubits. But currently, we also think of encoders and decoders for efficient quantum error correction. And this linear workflow still gives us a huge latency. So what people have done to optimize it is to get everything together, like the HPC power, for example, in the form of GPUs and the AI, together with the quantum circuit and form a logical QPU. Now, to make the figures a little 2D, because I will show some sequence models. So here we have our supercomputer. This is then at application time. And now I have my logical quantum processing unit. Here, the example I give is from NVIDIA QLink, because currently I don't know of any other system that can do things in this craziness. And the supercomputer now communicates with a real-time host, which is now embedded in the logical QPU. It has a real-time interconnect such that the quantum system controller and the real-time host are working in the same frequencies as the physical quantum processing unit. And what you see here is twofold. We have this FPGAs that allows us to control the signals that are directly communicating with QPUs. And therefore, we have like the very low latency real-time application. So how would now my sequence look like? Yeah. And I have taken this figure here from this paper. And what I also want to mention, I am not the expert on HPC, of course, but I hope I can bring this to you also closer. Let's look at this tight integrated workflow and level on the first level. And here we have our classical compiler that has our instructive set architecture, which encodes all our instructions that we want to send to our quantum processing unit. This is done on our supercomputer node, and then connecting to the real-time host, where the real-time host has the power of AI, for example, to connect with the controllers, the FPGAs. We are here, of course, it's NVIDIA CUDA kernel, and then control the quantum processing unit, but in a fixed session. Meaning that the quantum processing unit just gets its instructions, it works out the result, hands the result back. I do not communicate actually between the runtime of the physical GPU and I don't do anything during the execution. What is actually optimized only is the signals that I would give to my QPU, but this is predetermined. The more interesting part is then level 2, where we have our compilation phase, and the just-in-time compiler is now capable to run not only on the supercomputer, but also during the execution phase. And here what we need is a quantum computer that has a very long coherence time, meaning that errors will not inflict too much noise so that we can communicate with it. Given the real-time host and the GPU, we now want to evoke the quantum system controller to work closely with the quantum processing unit, giving us, in other words, the correct error codes, and also listen to feedback during the calculation of a quantum processing unit. Because what you might know is when you have a quantum model and you measure it, it collapses. But what you can do instead is not measure the whole quantum system, but only part of it, and retrieve information of the current process as some form of feedback. And this feedback can now be pushed into our quantum system controller or read out, be decoded with our quantum error correction AI that we do in these real-time RPs, and furthermore, change the next signals that I send to my physical GPU depending on this feedback. So what we say is that we measure our quantum processing unit during runtime, but not completely, such that we only get partial feedback of our operations. With all of this, we open technically a new paradigm beyond just quantum computing computational model. What we here have is something we call dissipative quantum computing model or non-Markovian computing model. And this allows us to redact or get information during computation. So a lot of problems are solved by just this tight integration of NVLink. And just to compare with this loose coupling where we just have the QPU as accelerator. So in the loose coupling, the architecture is we have our classical supercomputer, we send it to the quantum computer and retrieve it back to the classical computer. This is very bad for machine learning when you need to do the optimization of your graph of your neural network or quantum neural network on your classical machine, run it on a quantum computer, back and forth, back and forth. So training a mostly trivial quantum machine learning problem on real hardware can take you a week. And on actual HPC hardware, it takes you less than a minute. And this idea is hoped to be already solved with a tight integration, even on level 1, because now my setup is not sending something into the queue of my quantum processing unit. No, my logical QPU is technically also a system that can do classical operations, and then my queue has my batch file has also the instructions of what I need to do classical during or directly next to the computation. Yeah. So this would reduce quantum machine learning issues or of rather trivial problems to maybe a few hours of computation. But what is significantly more interesting is then, of course, when we have this tight interchange of feedback memory, because now we can find ways where we find algorithms that are on a better computational complexity than they are classically. And as I said already, the latency is then a huge issue in the loose coupling, which is days to minutes. And here we have seconds to microseconds. In level 2, we actually want like microseconds to be within this coherence time of a quantum computer. Yeah. So the current situation that we have here was investigated during the time where we said, like, okay, we have an HPC intensive simulation, and there are some parts that I can send to my quantum computer to accelerate. Yeah. But what we have seen in the last parts is just the amount that we need to, or the preparation time to make it feasible run on a quantum computer is too much that our quantum computing acceleration we would benefit from, yeah, especially if it's noisy. Here we do everything at once. Yeah? So algorithms can be dynamic, optimization can be done with AI calibration, and a lot of things that were previously an issue are not here, at least in theory, because currently we don't have the full NVQ-link everywhere available. Yeah? And what I want to tell you is that for any quantum machine learning setup, we need HPC in a very tight coupled integration, because otherwise we will never get any benefit. Yeah? Even if there is theoretical benefit on the quantum side. So, as I said, low latency and speed is something extremely important for us. Yeah? We need this seconds to microseconds communication. We need automation and reliability. We cannot always think of that a quantum computer can be calibrated for a whole day to run 1 hour and then be calibrated again a whole day to run the next hour. No, we need the automation to calibrate the system directly and best case live. One could argue like you want your quantum computer running the whole time. Yeah? So you have, if you get errors, they are similar errors. Yeah? The moment you allow the system to relax in some form, you end up with new forms of issues. What we want to have is then, with this kind of reliability and industry transformation, enabling us to use this new disruptive technology and therefore be now able to solve intractable problems. Especially what we already know is feasible is cryptography and the hope, and I say hope, machine learning beyond the classical limits. Why do we have to consider error correction? It's quite easy, because otherwise our quantum computer returns only noise. So the NISQ error, the noisy intermediate scale quantum error, which is expected to be not able to raise error rates below 10 to the power of -3, has the issue that if your problem scales or like with exponentially with the problem size, for example, 2 to the power of n, then small little errors which scale with 1 over 2, which are larger than 1 over 2 to the power of n, will just lead you to noise that we cannot optimize away in any form. So the model is technically not able to perform at all. So we are limited then to problems and of a certain size. The quantum advantage, therefore, is believed when we can control the error rates. And currently we use distance codes and surface codes, which scale with this distance d here, which in best cases are only the square root of the number of qubits that we need to consider. And then we get our advantage the moment we reach precisions beyond 10 to the power of 9, 10 to the power of -12. This actually also depends then on our problem size, because as I said, our problem is huge. We want to get 1 over this problem size as our precision to be able to still find the optimal state. Now, I said already, quantum machine learning needs this tight integration of HPC, and we need also quantum error correction. So is there current a benefit doing quantum machine learning so industry can directly use it today? The answer is not when you use a quantum computer currently, or at least when you use a quantum computer in the training process. Yeah. One solution, what people have came up is that we have possibilities to find setups where we can do quantum circuits in a reduced set, which we can simulate classically efficient. This reduced set of classically efficient will not yield us all the power of the quantum circuit, but in some cases it allows us to approximate loss functions that we need to do our optimization, especially in machine learning. Yeah. In these cases, what we can do is we can do a classical AI training, and then we need our quantum processing unit just to verify circuit samples. One thing that has become very prominent very recently is the generative quantum eigensolver, which uses an LLM to actually learn, and I say like the language of our quantum processor, which is nothing else than the circuits it needs to solve an issue. Yeah. And simulating these special circuits now is something that the quantum processor can do in linear time, but or in linear depth, but a classical computer needs exponential time. Yeah. And it has become very prominent. However, what you need to do is then train an LLM and to learn what circuit gates need to be applied, and then you need to come up with very cool and yeah, let's say innovative approaches to do your loss function. Another picture, and this is rather from a perspective of a physicist, and why I like the idea of this NVQ-link is because we have control of these pulse operations, and we can change them in time, we can change the signals. Yeah. And one thing I already mentioned before is these non-Markovian dynamics, which is technically not in the computing model of a quantum computer, goes actually beyond, as it's the communication of a classical system with a quantum system at the time. Yeah? And controlling this connection can give you actually speed ups, for example, in quantum annealing, where we do forced measurements or disturb our system in such a way that we can, for example, in this annealing case, get these gaps larger. And if we can get gaps larger, we can do computations with lesser precision or in less time to be able to solve solve optimization problems. And this is done with actually disturbing our physical QPU or asking with feedback, and this is a partial measurement from our system. So these problems we can only do if we have iterative steps, repeated local measurements, or in other words, like feedback. Other way around is that we can produce circuits which are hardware error resilient. This is a little bit weird at the beginning, but we can force our system to be in a subspace, or the evolution to be in a subspace where it is not affected by a lot of the noise effects that come due to temperature or due to many other interactions, for example, due to cables with our interconnect and quantum system controller. And I think with that, I'm already close to the end of my talk, because also of time. And what we have here is exponential speed ups that is our driving horse to do quantum machine learning, at least theoretically and from a fundamental perspective. But if we want to somehow make them possible, if it is possible actually, and here assuming very strong conditions on the problems, then we need these HPC workloads and workflows to do our linear algebra and factoring. Currently, hybrid algorithms are for sure necessary as to keep a quantum computer coherent for long enough time to solve problems that would take 3 days would otherwise be, I would argue currently with my knowledge and perspective, impossible. AI and HPC together solve therefore these real problem to a certain degree, because we haven't we have evidence that this works very good hand in hand. What we will need in the future is especially open platforms. And here I wrote together with NVLink, because there is technically not aware of any competition that could go beyond NVIDIA's ideas. But technically, to stay sovereign in Europe, we will also need to develop our ideas of these kind of tight integration and connect it with open platforms that we could already develop on NVLink. We have seen we need this fault-tolerant computing, but what we don't know is how long it will take to have these, let's say, logical qubits with error rates that we can get to quantum advantage. And quantum advantage, you can think of that we can execute an HHL algorithm with this given precision. Estimates say that in 5 years we are already that far. I am optimistic and say we hopefully this decade. And what is, on the other hand, very interesting is if we can prepare quantum systems that follow some fixed point and therefore correct themselves technically from emerging errors and self-optimizing therefore the system. And in best cases, they just need like some kicker, in other words, the signals that we control with AI during the runtime of our quantum processing unit and during the coherence times of it. And with that, I would like to thank you. And here is the whole group of mine, because I cannot get everyone on the same photo. Therefore, I decided to have this product state of some of my students and collaborators. Here, I would like to thank Sabine Müller, who has taught me a lot about HPC and is from Fraunhofer ITWM. And from the math department at RPTU, Alexei Bokharev, where we collaborate on multiple projects. Therefore, thank you very much for listening.
Thank you, Max. Thank you very much for this very interesting and realistic presentation. I will share my slide. Where is it? Okay, so it's time for questions. I don't see any questions for the moment, so please enter your questions in the question tool. Valeria, is there anything you wanted to add or maybe comment after Max's presentation?
I thought as a good moderator, I should have prepared some questions, but unfortunately, some of them were already taken out of my hand. And I think what Max was kind of emphasizing here was that the only tool he knows at the moment for the low latency is the NVQ-link from NVIDIA. So I think that is a warning sign for us now here in Europe that that's the only tool. And there's a lot of progress which has been made in the past year. And it's wonderful progress for the quantum computing community, but I think it's a bit of a warning sign. And the second question, because you were mentioning some ideas, but what is your pathway towards these early fault-tolerant algorithms? I mean, before being fault-tolerant, how would you propose this transition between the current algorithms and the fault-tolerant algorithms?
So my favorite version is something that I also developed during my PhD. And this is the open system ideas, exactly where a system interacts with its environment. And the quantum system interacts with its classical environment. So what I had looked so far into during my PhD thesis was rather models which can be modeled in the form of Markovian dynamics. And here we can show that we can get also noisy algorithms or noisy quantum computers with guarantee to a certain state, which can be a ground state. What we need to make sure is that our system has like an error rate lower than our driving force of these dissipations. So here the hope is that we have early fault-tolerant quantum computers which are not yet able to get any form of quantum advantage because they cannot compute HHL algorithms or so on, but are already less error prone, such that our algorithms become truly error resilient. So if an error happens, then during our algorithm, it's corrected directly away, and it is not an issue anymore. So this is something that I'm currently looking at, and it changes sometimes the computational model, especially if you think of non-unitary evolutions of your system. The issue that we have is a quantum computer is also struggling sometimes to compute these problems. So it's even worse to simulate than the quantum system. But it gives us hope that if we, for example, have access like now with this low latency, that we can tune a resonator to behave with some form of error rate or very weird, interesting interactions to actually force our system to have these non-unitary evolutions and therefore be able to go beyond current computation strategies.
Okay.
Thank you, Max. So we have one question from Baris Malcioglu. It's in the chat. You can see it. Will tight integration tools in development work for measurement-based quantum computing?
I hope so. So the one big issue currently, if you have measurement-based algorithms or partial measurements of your system, is that you wait a second for this code to execute on your quantum hardware, and then the rest of the system has become decoherent, and therefore your intermediate measurements that you have done lead the system to be not available very much. So just having this tight integration allows us probably to do this significantly faster, and therefore be able to do also measurement-based quantum computing. And maybe I would like to ask a question back here, because measurement-based quantum computing I understood now as intermediate measurements, but it could be also that you start from a large quantum state and introduce rotations and measurements such that you retrieve your results. So my question back is, do you want was your question about intermediate measurements or about measurement-based systems or full measurement-based systems?
Actually, Barris, I don't know if it's another question or an addition to this one. He said, how about dynamic models such as flow-K engineering, etc.? Will they be possible with a kernel-based approach, or AI decoders will prevent such use cases?
Actually, I think AI use will allow us to do flow-K cases, actually. Flow-K, for people who are not so familiar, is the periodic driving our systems. And this is, of course, necessary that my driver is of the same frequency or can operate within the frequency of my quantum processing unit. So here, I think this is an enabling technology that allows us to do such things.
Okay, sorry.
Sorry, Valeria, please go ahead.
There is another question from Petrus Santis going more into these different modalities. And he is asking, how do you believe the low latency approach has to be adapted for different qubit modalities, such as superconducting with gates in order of nanoseconds, atoms and ions with gates in order of microseconds, and so on?
So this is a very good question. We have a lot of different possible quantum computing like hardware. We have neutral atoms, which have frequencies that are 10 to the power of, frequencies 10 to the power of minus, 10 to the power of 2, like kilohertz. They are quite slow. We have the superconducting qubits, which I think was written in nanoseconds. This is only for a few gates where we can do it in nanoseconds. If we do most of the quantum computing stuff, it's closer to milliseconds for the operations. And therefore, we currently can control these systems. It's feasible. If we think of light or quantum computing with light, then we have a different problem, because our signal strategy, our GPUs would simply not be fast enough to do such a thing, or we need our photon system to be working for longer times. So I don't have a full answer to this question, besides that for different problems we should use different hardware to do different things, and we benefit differently from them. Okay.
Then there is a question from Fabrizio Maguliani. Is there any interest from key ISV independent software vendors to evaluate how to integrate quantum computing in their applications?
I think so. One thing that is in my mind, because I have been in some recent workshops and talks. This is so-called QC eval, I think. Give me a second, then I can tell you if I find it really quick. I think it's QC eval, which concludes, QCal eval is, I think, the wait. And there are multiple QPU vendors, as well as networking partners that help to find experimental significant and calibration, experiment significant problems, and allow for combined calibration, diagnosis, and these kind of things. I hope this is your question.
And then Fabrizio again, well, actually, he asks you to comment on this affirmation. Quantum computing will have success when available in PCIe form factor. It's form factor, not from factor. Any comments on this? Is this true, or?
Let's say we have to be careful here, right? There has been one solution that you could have put in your classical computer in this PCIe form factor. It simply did not work. So from this perspective, it will have success, I would argue, when we can put it in racks, in clusters, which we can do already, but we still need quantum error correction to do actual algorithms that are expected to perform faster. If we cannot do it,
if I could add a little bit here, because I think there has been also much more success in the past years. So I remember with the NV diamond approaches that they were going very quickly towards racks, but it seems that there's a bit of a scalability problem up to now with these approaches. However, what I've seen in Hamburg recently, and just because I am in Hamburg, maybe it's in other places too, was this factorization that you really miniaturize technologies which deemed not to be so scalable, such as ion traps, and we're putting it more into chip-like structures. And how that happened was that they were really working together with people who were coming from the embedded system side of things, and they have been working together with the quantum computer experts, with the hardware experts in quantum computing. And I think that this is something where ETP4HPC has the people who should think about such solutions, because here we are at the right place where you could go and see with your expertise how you can handle such cases, because suddenly things get much more scalable when HPC people look at stuff. And also from an architecture point of view of how quantum computers work. And that would be very helpful for other technologies.
So the next question, I think.
Yeah, and then there is actually it's some additional information from Barris. I was referring to one-way computing, how some hard on HPC QML algorithms become easy on HPC with that model, and he's sending a link to a paper.
Yeah, I'm familiar with the paper from Maria Schult and I think Maria Schult and Kilhuran. 1 second. At least Maria Schult is on it. And then the paper is formulating a question which fits the zeitgeist of quantum machine learning and the debate if there's any benefit from it. What we currently cannot say is if there will be any benefit from a perspective of doing classical work on a quantum machine, on a quantum computer, because we have these humongous overheads from writing data into our system and writing it out, though it becomes better. But the paradigm is that we could use quantum machine learning directly in quantum systems where the readout hinders us to get all information that the quantum model would give us technically for free. And what would this change from this perspective is that we could do quantum sensing significantly better, that we could do maybe quantum communication better, just from our quantum machine learning model being embedded or part of our sensor or part of our communication channel. So
may I also add a little bit on that? I mean, like, in my opinion, what we also should think about is the energy aspect of quantum computing, because right now we are building power plants in order to do our ML models classically. And here, even though there might not be such an advantage in speed, it might be an advantage in energy, which could also drive QML here.
I agree.
Yeah, good point. So then we have a question from Max Huzarov. Most discussions around quantum ML focus on models or potential advantages. Sorry, in your experience, where does real value appear today? In the models themselves or in how they are integrated into systems? For example, execution control, hybrid workflows, reproducibility.
So what I can tell you from my own experience is when we actually do not include a real quantum computer in our process. So when we reduce our operations that we previously saw very helpful to the minimum set that we can compute on a classical computer efficiently. So-called quantum-inspired algorithms, and these also include tools like tensor networks, just work and they work significantly well. In a lot of cases where I've seen any form of quantum advantage, it was not due to the difficult property of entanglement being used during the simulation of the problem, but rather its stochastic nature, its form of changes like some weird random augmentations on my data set, which just were helpful beyond what we expected before. Here we have publications, for example, where we just simulated quantum rotation gates, which do not change any entanglement. And we did some benchmarking on classification of ImageNet, so non-trivial data sets. And we found out that just doing the part without entanglement is already significantly beneficial, actually better than employing a quantum computer or quantum neural network at the moment. So I would say the next 3 years is probably the day of the quantum-inspired approaches. And then probably will be the time of the hybrid workflows, maybe 3 or 5 years. And later, I don't think that there will be an end-to-end quantum model. So from my experience, it makes also no sense because we end up with very weird restrictions in end-to-end systems. So I hope I cannot see much more into the future currently. Changes are crazy in this field.
Yeah, well, you've been recorded, Max, so we'll check again in a few years' time if your predictions were correct.
Let's see also how many enemies I have by just saying that currently just excluding the quantum computer is a
Okay.
better option.
Well, I don't see any other questions coming in, and anyway, it's going to be time soon, so I think we can close for now. I would like to thank you both for being here today. I think I enjoyed very much this webinar. I think everybody else enjoyed it too. We had a very good audience today. Max, Valeria, is there anything you wanted to add before we close?
No, I think Max was really saying the right kind of sentences to close the seminar, and that was amazing. So nothing to add.
Okay, so our next webinar is in May, on the 22nd of May. It will be a completely different topic on open source and digital sovereignty, and you will receive an invitation very soon. We are working on it, but the date is set. So Max, a big thank you, really. It was a great webinar. As I said, I enjoyed it very much. Valeria, thank you for putting us in touch with Max, because that was a great idea. And well, good luck for your SRA, for your work on the SRA, because Valeria is the co-lead of the ETP4HPC working group on quantum computing and HPC. So they are only just starting, so a lot of work ahead.
Yes.
So thank you both, and well, thank you everyone for being here, and talk to you soon, I hope. Thank you.